All right. Hello, everyone. Today is April 1st, Thursday. It's a Thursday early morning, and I'm going to take lecture videos one by one. Um, Hope you guys are doing well, stay healthy, and enjoying the spring semester. Uh, so this week, my aim is to cover Chapter 17 in Musgrave Winston Green. That is about the positive theory of equilibrium. So in Chapter 16, we studied the normative theory of equilibrium. So we studied two welfare properties of equilibrium, and we went into Pareto efficiency. So we studied several properties of Pareto efficient allocation by linking to social welfare maximization problem and by driving first order conditions characterizing the Pareto efficient allocation. So that is about the normative theory. If we have an equilibrium, what kind of properties equilibrium, does have to have? Yeah? So it's more like what it ought to be. So it's more like a normative theory. If the equilibrium exists, the equilibrium must have or must possess that kind of properties. So chapter 16 concerns the normative theory of equilibrium. On the other hand, chapter 17 concerns the positive or descriptive theory of equilibrium. So now we describe the economy. So we describe the equilibrium behavior as it is. Okay? Uh, Chapter 17 consists of several topics. There are so many materials in chapter 17 in the textbook, but I'm going to sort of the most important ones. So the key essence about the positive theory of equilibrium and trying to make some videos regarding those. And first, I'm going to talk about equilibrium. So we defined the equilibrium already, but just to remind you of the definition, I'm going to show the exact definition of equilibrium. And we are going to analyze that equilibrium and to see what kind of a prediction we can make from the general equilibrium model. So we study a predictive power of the general equilibrium model in chapter 17. Okay? And for this purpose, I introduced the notion of excess demand function. That is a primary tool for our subsequent equilibrium analysis. And using this excess demand function, we characterize a Walrasian equilibrium. So excess demand function enables us to characterize equilibrium as a solution to system of the equations. So that is a really convenient tool for finding equilibrium. And we are going to study several properties of excess demand function as well. All right, and then the second topic is about the existence, because the existence topic is a little bit tedious but very important topic in economic theory, because if we don't know whether equilibrium exists or not, then we analyze such a thing that may exist or may not exist. So then our analysis is kind of useless. So we have to establish the for positive theory of something. We have to establish existence first. Existence is existence. Okay? So we are going to talk about existence as well. The third topic is the uniqueness of equilibrium. If there exists a multiple equilibria, there are so many equilibria, then of course the prediction power is going to be weak. So to strengthen the predictive power, we are going to see under which conditions equilibrium turns out to be unique. And the last topic is stability. So the equilibrium is defined as a stable status, but some equilibrium is a stable. So even though there is some external force that may affect a equilibrium, if the equilibrium is stable, then it does not change that much. But if the equilibrium is unstable, then even with a small economic external force, it changes a lot. So we are going to talk about stability of equilibrium just a little bit, all right? So chapter 17 is comprised of those 4 topics, and I'm going to explain one by one, okay? And in this first video, I'm going to talk about equilibrium, the very first topic. So we are going to see what is this excess demand function and why that is a convenient tool for the analysis, for the equilibrium analysis, and how do we characterize equilibrium with this excess demand function. We also study their properties. All right. So let me start with the definition of equilibrium. So we have seen this in the previous lecture slide, but just to remind you of that equilibrium definition, let me go over that. So the general framework, the so-called private ownership economy, is specified by those 5 components. So we have 3 components about consumers' characteristics. So each consumer I, or individual I, is characterized by his consumption set, what kind of bundles consumer I can choose, and his preference relation, between 2 bundles, which bundle individual I prefers. And theta I, so because in the presence of production, every firm is owned by a set of individuals, a set of consumers. So in the presence of production, we have to specify each consumer's share in the firm, in each firm. So theta I stands for consumer I's shares in several firms. And there are producers, there are firms, there are J firms total, and each firm's production technology is described by a production set. So once again, production set is the set of all feasible production plans. So that describes, that is a one way to describe from J's production technology. And finally, we have to specify the initial endowment of the economy, what this economy has, what kind of resource this economy has at the outset. So those are 5 components specify one general equilibrium model or one private ownership economy. Okay? And we defined Walrasian equilibrium. Walrasian equilibrium, also called as competitive market equilibrium or price-taking equilibrium, when we highlight the price-taking behavior. That is together with market completeness, price-taking behavior is a very crucial assumption, very significant assumption in this general equilibrium model, general equilibrium analysis. So under the 2 assumptions, market completeness, every good, every resource can be priced. So we can think of a price for every resource. That is a market completeness. And the second assumption was every economic agent, so even firms and even consumers, both economic agents have no market power, have no power to control the market price. So market price is solely determined by competition in markets. That was those 2 were 2 main characteristics, 2 main assumptions in the analysis of market mechanism. Right? And then, so in that market mechanism, we define the equilibrium as a pair of allocations. So allocation for consumers, X star. So each component of X star stands for each individual's demand schedule, or their consumption behavior, or their choice of a bundle. And each Y star stands for each firm's choice of input output. So in other words, each firm's production plan. Okay? And price factor. So the price of each commodity, P star. So equilibrium is defined by these 3 tuple elements. Right? And then for these elements to be in equilibrium, they have to satisfy these 3 conditions. First, from J's production plan to maximize from J's profit. So we can rewrite this so we can formulate the one mathematical equation that describes this profit maximization condition. This condition can be written as given price vector P star, and if we multiply by yj star using the dot product, and it stands for that represents the firm J's profit from this production plan, and it should be higher than so production plan yj star should yield higher profit than any other feasible production plans. So P star dot yj for every feasible plan yj, so in firm J's production set. That is the first condition. That is a one main condition on y star, this allocation vector. And for x star, each individual i's choice of bundle should maximize individual i's utility given his or her budget constraint. So I can write this, say, I can formulate the second condition as ui using the utility function. So individual i's utility should be maximized at x star I. So ui must be maximized at x star I, meaning that for every xi in individual i's budget set, so that is a utility maximization condition. And the i's budget set can be written as, in this private ownership economy, consumer i's budget set bi, that depends on price factor, and the consumer i's initial endowment, omega I. It is a set of affordable bundles. So first, it has to belong to consumption set of possible bundles, such that in order to choose xi, so in order to make it possible to choose xi, the total expenditure for choosing this xi cannot exceed consumer i's wealth, but the wealth can be written as in this economy. First, the consumer I has an initial endowment omega I. So we have to count the market value of the initial endowment. Also, we have to take into account because every individual has a share. So that means individual I retains the right to take some part of the profit in firm J. So individual I has a share of theta ji in firm J, and firm J makes a profit of yj star. Okay. So that is a total profit generated by firm J at this maximum profit generated by firm J at this price factor. So because individual I has a share of theta ji, so individual I retains the right to take this profit. Okay? A part of profit as much as his share. And there are J firms, so we have to sum. So wealth from holding shares. From J is equal to J. J goes from 1 to capital J. So that is a budget set. We can regard this expression on the right-hand side as consumer I's wealth in private ownership economy. Right, so that is the second condition, and the last condition bears on the price factor. The price factor must clear the market, and because we have a total L commodities, and for each commodity K, aggregate demand for commodity K, that is each individual at this allocation X star, each individual consumes X sub Ki, so that is the individual I's demand for commodity K, and we add up this X from I equal to 1 to capital I, because there are total capital I consumers. So it is a aggregate demand for commodity K, and it should be equal to, first we have to think about the initial endowment. So omega K bar, commodity K's initial endowment, plus, because there is a production, commodity K may be produced or may be used for production. So we have to take into account production as well. So YKG, that is a J from J's production of commodity K, or J's use of commodity K for input as a input. We have to sum this YKJ over from J. So J equal to 1 to capital J. So the expression on the right-hand side, aggregate supply of commodity K, and this is aggregate demand for commodity K. So for each commodity K, this market clearing condition has to be met. So price is determined by, so the equilibrium price is determined by this market clearing condition, because the demand schedule and the production plan depends on P. So using this equation, the total L equations, we can find out price vector P. So we're going to study how to find the equilibrium price in a simple example. All right, so that is the formal definition of Walrasian equilibrium in the general framework, the so-called private ownership economy. But we start our analysis in a simple model. Okay? So, in order to introduce excess demand function, that is a primary tool for equilibrium analysis. So we are going to start from the simple model that is a pure exchange economy. So in chapter 15, we've already seen 2x2 pure exchange economy, where there are two consumers and there are two goods. But we generalize that model a little bit. Now we assume there are I consumers and there are L goods. Okay? And in this economy, so we abstract away production process, and we just pay attention to exchange, the exchange activities between among I consumers, and we study how equilibrium prices are determined by such an activities in markets. Right, so we start with a pure exchange economy in which I consumers trade their endowments. Right. So here, going back to the previous definition, so we don't have to think about the production. And so there is a no YJ, so there is a no firm shares. So we can delete these two components from our consideration. We have to, so for characterization of equilibrium, we have to think of these two conditions, whether allocation X and the price vector P satisfy these two conditions or not. Yeah, so the equilibrium, allocation X star, and P star will be determined by these two conditions in a pure exchange economy. So the utility maximization condition can be written as, because now we don't have to consider this part. Yeah? So it can be written as consumer I's bundle to maximize consumer I's utility for every I or every xi in the set pi p star omega I, the consumer I's budget set. Now that can be written as set of possible choices such that the bundle must be affordable. So we can write this way. Right, so utility maximization for every consumer I, and remember there are total capital I consumers. And also for each commodity, market must clear. So the aggregate demand for commodity K, and we don't have any production process in this economy, so disregarding YKG, so market clearing conditions simply written as this. So I use the inequality because to allow for a possibility that commodity K is a neutral good. Okay? So if every commodity K is desirable, so every consumer wants that good if the price is not that high, meaning that consumers' preference relations are monotone or strongly monotone. Okay? Then the market clearing condition is going to be equal to each other. But if commodity K is a neutral good, so nobody cares about that. Okay? Then the price is equal to zero, okay? And the aggregate demand may be lower than the initial endowment. Okay? So this inequality holds with an equality, should be equal to each other if commodity K is desirable. In other words, if preference relation is strongly monotone for every consumer, every I. Okay, so that inequality is just for allowing for a possibility that some commodities are neutral goods. All right, and one more thing we have to notice is if the preference relation is strictly convex, and so if the preference relation is strictly convex, then indifference curve has a strongly convex toward the origin. So there is just a one single point. So there is just a one single point at which indifference curve is tangent to margin line. If the preference relation is not strictly convex but just a weakly convex, then indifference curve may indifference curve may be parallel to this margin line. So we have several points at which indifference curve is tangent to the margin line, meaning that demand function, the optimal demand schedule is not a function, so it's not a single valued, but it's is a correspondence, so is a multiple valued. Okay? The strictly convex function, the one implication of strictly convexity is a optimal choice, consumer i's optimal choice at each price vector. Okay? So given price vector P, and P dot omega I is a consumer i's wealth in this pure exchange economy. So given price vector, given his wealth, xi, consumer i's optimal demand is going to be a function, is going to be a single valued. Okay? So extra I, the bundle maximizing consumer i's utility is going to be consumer i's demand function. So the first condition can be written as consumer i's choice is a just that comes from consumer i's demand function. All right, now we are ready to define excess demand function. So once again, this function plays a pivotal role in our equilibrium analysis. So the excess demand function of a consumer I definition is really simple. So excess demand function is denoted by Zi, given price vector P, that is consumer i's demand, and we subtract away consumer i's endowment. Excess demand, literally means consumer i's excess demand for every commodity. So xi indicates i's demand function. So under the assumption preference relation is strictly convex, we can write the consumer i's demand as a function, as a demand function, not demand correspondence, but a demand function. So this demand, excess demand, can be defined as a function as well, because this is a function, single valued, and consumer i's initial endowment is a constant. So there, just the difference is going to be a function. If xi was a correspondence, then is ci also be is going to be a correspondence as well. So that is a excess demand function for each individual. Let me do one example to help you understand this notion. So suppose that consumer A's preference relation is represented by this utility function. So that utility function represents consumer A's preference relation. That is given by a linear function, meaning that good 1, good 2, to consumer A are totally substitutable. Totally substitutable. So total substitutes. Okay? At the fixed ratio, and consumer A's initial endowment is given by 2 and 3. Initially, consumer A has 2 units of good 1 and 3 units of good 2. And in this example, we can compute the excess demand function because, all right, so consumer A's utility is 2x1A plus x2A. Okay. So for linear functions, indifference curve is going to be linear like this. So, optimal solution is determined at the corner. Yeah, so at this corner or at this corner. So now we have to compare consumer A's MRS between two goods. The marginal rate of substitution between 1 and 2 is going to be 2 over 1, so that is 2. And you should compare that with a relative price, P1 over P2. Let me call this just a P. Yeah? So if 2 is larger than P, consumer's MRS is higher than given the present relative price. And consumer A's optimal choice is, as a consumer A's subjective evaluation of good 1 is that is an interpretation of MRS. Consumer 1 is willing to trade these two goods, 1 and 2, at the ratio of 1 and 2. Yeah? So with 2 units of good 2, consumer 1 is willing to give up 1 unit of good 1. Okay? That is MRS. And relative price is a objective exchange ratio in market. So if 2 is higher than P, then consumer 1 is willing to just purchase good 1. So X1A is going to be now we have to think about consumer A's wealth. Consumer A initially has 2 units of good 1, 3 units of good 2. So the market value of that initial endowment is, given this price, relative price P, can be written as 2P plus 3. That is consumer A's wealth. Right? So 2 units of good 1, 3 units of good 2, and we normalize price of a good 2 by 1, just thinking about the relative price. So the consumer A's wealth can be written as 2P plus 3. And so he's going to spend all the wealth on consumption of good 1, so we can just simply divide it by P1. Right? Just a second. I think normalization, it seems better to normalize P2 after finding the demand function. So let me write the consumer A's wealth as a function of P1 and P2. So 2P1 plus 3P2. So 2P1 plus 3P2. And X to A. Consumer A does not consume the 2. But if 2 is lower than P, now consumer A does not consume good 1. And all the wealth, all of his wealth on good 2. So we have this, right? And I'd like to use this relative price. So let me do some algebra here. X1A, when P is lower than 2, P is lower than 2, can be written as 2 plus 3 times P2 over P1. That is a P inverse, reciprocal of P. So P to the power negative 1. And X to A, when P is higher than 2, can be written as 2P in terms of P plus 3. Okay, then excess demand function. So consumer A's excess demand for good 1 given P. Of course, when 2 is equal to P, so MRS is exactly the same as relative price, then so every bundle on the budget line is going to be optimal. So I can write this when 2 is equal to 2, every bundle. So now we have the set of bundles X1A, X2A, such that P1, X1A, P2, X2A equals 2P1 plus 3P2. Because when P is equal to 2, that's the case when indifference curve is completely overlapped with the budget line, right? So every bundle on the budget line is going to be optimal. We have this. All right, now we are ready to find the excess demand function. So let me write the excess demand function as a function of P. Yeah, so this P is a P1 over P2. So Z of P, consumer A's excess demand for good 1 is going to be, now that is a piecewise function when when P is lower than 2, when P is lower than 2, his demand is 2 plus 3 P to the negative 1. that is a X1A, minus consumer A has a initial endowment 2 units of good 1. Okay, so 2 will be cancelled. So 3p to the power negative 1 is going to be excess demand function. Now when p is higher than 2, then it's going to be negative 2. If p is equal to 2, then the excess demand function, I say not that easy to write, but let me write down later. But excess demand function to 2. So when p is lower than 2, that is negative 3. When p is higher than 2, then 2p plus 3 minus 3, so it's going to be 2p. Okay? And finally, when p is equal to 2, now excess demand function, ZA, is going to be 2 tuple. So one pair of functions, Z1A and Z2A. So now it is the set. So that's going to be the set of these two functions such that P1, so P1 is 2. So 2 times Z1A plus Z2A is equal to 0. So that is a excess demand function for consumer A when consumer A's preference is represented by this utility function, and when consumer A has an initial endowment 2, 3. Okay? So this Zi is a vector. In case of L commodities, Zi of P is going to be a vector. So Z sub 1 IP. Consumer I is excess demand for good 1 and for good 2 and so on. Okay? And then we can think of, so now we can define aggregate excess demand function of the economy. So just by aggregating each consumer's excess demand function. So without the superscript I, Z of P is just a summation of ZIP across consumers. So if we have just the two consumers, consumer 1 and consumer 2, Z1, 2 of P, consumer 2's excess demand for good 2, and consumer 2's excess demand function for good L. Okay, so we add these two vectors component-wise. So aggregate demand Z of P is going to be, the first element is Z11 plus Z12. So let me call this Z1, right? Z11 plus Z12. So that is a aggregate demand function, aggregate excess demand function of good 1. And the sum of these, the second components, Z21 plus Z22. Let me call this Z2P. The aggregate excess demand function of good 2, and so on, and etc. So ZL of P. Okay? So for subscript, for each commodity K, Z sub K of P is a Z sub K I of P. So the summation of Z sub K I of P, where I goes from 1 to I. Okay? So that is a summation of each individual's excess demand function for good K. Okay? So it tells us aggregate excess demand for good K. All right. So that is the excess demand function. And the way to interpret this is if excess demand function is positive, yeah, then there will be a excess demand. And if that is a negative, then there will be excess supply, in the sense that initial endowment is not exhausted by consumer I, right? And if that is equal to zero, then supply, and there will be neither excess demand there will be neither excess demand nor excess supply. So that is the way to interpret. And now, why excess demand function is useful? Because a excess demand function enables us to characterize equilibrium in full, just with a single equation. The proposition 3.1 is quite useful, but proof is a very straightforward. So it tells us in pure exchange economy, where each consumer I's preference relation is strictly convex. We need this because, once again, without strict convexity, we can't think of a consumer I's demand function. It's going to be demand correspondence. So the associated excess demand will be a correspondence as well. So it's not easy to define. We can define excess demand function without strict convexity. And we also need a locally non-satiation. That is a necessary condition. So locally non-satiation just allows for, but that is a little bit weaker assumption that strong monotonicity. Just if a preference relation is strongly monotone, meaning that every consumer, so the more the better, applies to every consumer. But the local non-satiation is slightly weaker than strongly monotone. In the sense that it allows for some goods are neutral goods. Okay? Not every good, but some good is a neutral good. So local non-satiation accommodates some neutral goods. But in case of strong monotonicity, so in case of strongly monotone preference relation, every good is a desirable good. So with this weaker condition, if P star is a Walrasian equilibrium price factor, okay, then excess demand function must be non-positive. And the other way, so if a Z of P star at this price factor, excess demand function is non-positive, and P star is going to be Walrasian equilibrium vector. This is a if and only if statement. So this condition, aggregate excess demand function be non-positive, is a sufficient and necessary condition for price vector P star to be an equilibrium. Yeah, so this is useful. So that is a system of, so we have a system of, inequalities or a system of functions, because aggregate excess demand function has a L elements. So that is a L tuple vector, aggregate excess demand for commodity 1, for commodity 2, and through the commodity L. So for each commodity K, excess demand function, aggregate excess demand function is a non-positive, so less than 0, and P star is going to be a Walrasian equilibrium price factor. With a strong monotonicity, so with a strict convexity and strongly monotone. So if we impose a more strong assumption than local non-satiation, strong monotonicity, then this equilibrium condition is held with an equality. The P star is a Walrasian equilibrium price factor if and only if aggregate excess demand function boils down to zero at that price factor. That is exactly market clearing condition. That is quite intuitive because strongly monotone, in case of a strongly monotone preference relation, every good is desirable and there will be no excess demand. There will be no excess supply. If some good is left for free, and some consumers will consume that. So there is no chance that we have this one. So initial endowment is not totally exhausted. So some part of initial endowment is left for free. Yeah? That kind of situation cannot occur as an equilibrium if every good is desirable. But if some goods are neutral, then there might be some chance that good K, if K is a neutral, then there we may have excess supply. Right. So the proof is very simple because that is immediate from the two conditions of equilibrium. So we have a utility maximization condition for equilibrium in pure exchange economy and the market clearing condition. But market clearing condition is simply means that aggregate excess demand function. This is an aggregate demand for a good K, this one. And this one is an aggregate supply in the absence of production. So in terms of aggregate excess demand function, this inequality can be written as Z sub K of P is lower than zero, lower than equal to zero, right? So by the second condition, if P star is a Walrasian equilibrium price, it must obey the second condition. So for each commodity K, aggregate excess demand function should be non-positive. So we have this. Yeah, so we have this condition. So this condition is necessary for Walrasian equilibrium. Now, in order to prove the converse, suppose that we have this condition. So we have a one price vector at which aggregate excess demand function is non-positive. Okay? And now the only thing we have to do is, because equilibrium is defined as a one allocation vector and price vector. Okay? So the only thing we have to do is, at that price vector P star, we have to find one allocation, and that allocation indeed maximizes each consumer's utility. And we can say that allocation and price vector constitute one Walrasian equilibrium. So here, given P star, and this P star determines a one price vector, and at the same time, each consumer's market value. So the market value of each consumer's initial endowment. So I forgot the attached P star here. So if we have a one price vector P star, then we can think of, because under strictly convexity, we can specify each consumer's demand for each good. So individualized demand for good one, that is a one number given this P star. So P star determines a market value of his initial endowment. Okay? And then demand for good 2, demand for good L. So this way, we can choose a one allocation from the demand function. And then this is a demand function. So by definition, x1i, so the x star I, should maximize consumerized utility given at this price vector, P star. Okay, so consumer I is optimal bundle, and consumer 1 is optimal bundle, and consumer I is optimal bundle. So if we put together those bundles and to make a one allocation for the economy, and this x star and the price vector P star will satisfy the two equilibrium conditions. Therefore, they constitute a Walrasian equilibrium. So this statement is a very easy to prove. It's not that profound proof, but it's quite useful because uh, if we want to see one price vector is a equilibrium or not, we can just compute the aggregate excess demand function and whether that takes a non-positive value. Okay? It is an equilibrium. Otherwise, it's not an equilibrium. Because this is an if and only if statement. It gives us a full characterization of equilibrium price vector. All right, then let me talk about the properties of excess demand function. So once again, excess demand function is a L tuple vector. So price vector is also L tuple vector because if we have a L goods, we need a price of a good 1, price of a good 2, and price of a good L. Right? And for each commodity, there is a aggregate excess demand function. Excess demand function is a L tuple vector. Okay? And we maintain these two assumptions. Every consumer's preference relation is strictly convex and locally non-satiated, right? And we assume, let me change this, not locally non-satiated, but now let me impose a more strong assumption, strongly monotone. That is a typo. Strongly monotone. So because just with a local non-satiation, we can't prove Wallace law. So the exact statement is preference relation is strictly convex and strongly monotone for every consumer I, and the initial endowment is strictly positive. Okay? So every good K has a initial endowment, strictly positive initial endowment, right? And the excess demand function satisfies the following properties. First, it's continuous and homogeneous of degree 0. Continuity comes from the one mathematical result, the so-called Burgess maximum theory. So Burgess maximum theory tells us if we have a function f of x, say t, right, and we maximize this function over x, and x has to be in the set capital X. Okay, so x is a choice variable, and capital X represents the order of possible choices, right? And if x, capital X, this set is a compact and convex, okay, then so if the set of possible choices is compact and convex, and the function f, objective function f, is continuous and quasi-concave or strictly quasi-concave, so that is a equivalent to preference relation is strictly convex. I mean, if preference relation is strictly convex, consumer I's utility function, so the objective function in this maximization problem, is going to be strictly quasi-concave. Okay? It's just a convex, then quasi-concave, right? But the Burgess maximum theory tells us choice set is compact and convex, right? Think about the Burgess set. Burgess set is a compact set, is bounded and closed set, and convex, right? The Burgess set satisfies these two conditions, and utility function is continuous and strictly quasi-concave as long as preference relation is strictly convex. So if these assumptions are satisfied, then the maximum x star of t is, so then x star t, which is a solution. So f of x star t and t is a value function of this objective function. So x star t is a solution to this maximization problem. So is going to be is a continuous function of t. So it means as t changes, the optimal solution changes smoothly. Yeah? It does not change abruptly. It changes continuously. Yeah? So here t is a parameter. In utility maximization problem, t is going to be price factor. Okay? And the x star, that is a optimal choice. And remember, with strictly convexity, optimal choice is a single valued. We do not have a correspondence, but a function single valued for each price factor. The optimal choice is going to be a function of a price factor, and by Burgess maximum theory, it is a continuous function. All right, so this Burgess maximum theory is often used for continuity of demand function whenever we have a quasi-concavity, strict quasi-concavity. All right, so by Burgess maximum theorem, demand function is continuous. You may refer to chapter 3.d for a more detailed discussion about this. So xi is a continuous, and excess demand function is nothing but difference between demand function and constant initial endowment. It will be continuous. So continuity is immediate from Burgess maximum theorem. And furthermore, in pure exchange economy, demand function is homogeneous of degree 0 because budget set. So in pure exchange economy, the budget set is this. So if we just scale up price factor and wealth by multiplying by alpha, yeah, then there is a no change in the budget set. So there is a no change in the optimal choice. X star will be the same because the budget set is the same. Okay? So the demand function is a homogeneous of degree 0. If we multiply price factor and wealth by alpha, okay? So excess demand function is also homogeneous of degree 0. Because even though we scale up by alpha, demand function does not change at all. It is invariant to scalar multiple. So the DI function, excess demand function, is also homogeneous of degree 0. Right? So the first statement is done. Now the second property, excess demand function satisfies Wallace law, meaning that for any price factor, I want to highlight that this law holds for every price factor, every vector P. I already highlighted here. For all price vectors P strictly positive, we have this. The dot product between price vector and the excess demand function should be equal to 0. So the way to see this is, and remember, with a strongly monotonicity, strong monotone, whenever preference relation is strongly monotone, then we have we have this. Consumer's I budget constraint must be binding, or wealth should be exhausted for consumption of some goods, because every good is desirable. If there is some money left, that means his choice consumer I's choice is not a optimal choice. In case of a local non-satiation, there might be a chance that some money is left, because in case of a neutral good, yeah, that does not increase my utility, and why do I have to spend money on that, right? In such a case, there might be a chance that some money is left, but in case of a strongly monotone, there is no such a chance, meaning that consumer I's budget constraint must be binding at the optimal choice. Okay? So with this, so in pure exchange economy, in case of two goods, that means P1, say X1, P2, X2 must be equal to P1 omega 1, P2 omega 2. So so the market value of the consumer's initial endowment should be equal to total expenditure. Budget constraint must be binding whenever consumer's preference relation is strongly monotone. So we can rewrite this as P1 x1 minus omega 1, P2 x2 minus omega 2 is equal to 0. Okay? And using excess demand function, can rewrite this Z1, Z2 is equal to 0. All right? In case of two goods. And in case of three goods, now P3x3 on the left-hand side and P3 omega 3 on the right-hand side. In case of L goods, now we have this. So for each commodity K, Pk times Zk, or consumer I's demand minus his initial endowment of a good K. So the product between these two and the summation over K, good K, should be equal to 0 for every consumer I. Okay? So for every consumer I, we have a zero equation. So we can just sum up for all consumers, because for every I, this one is equal to 0. We just add up I zeros, that is still 0. Okay? Now we interchange the summations, the order of summations. We first take a summation over I, and then take the summation over K. Okay? And Pk, that is independent of I, so we can pull it out. So this one can be written as summation over K and Pk and summation over I and xki minus omega ki. Right? And then after rewriting this equation, and this is going to be summation of I, excess demand function for good K, that is a Z sub K. Aggregate excess demand function of good K. And then we multiply by Pk, and then take the summation of over K. That is a P dot, the dot product definition, P dot Z of P. Right? Because P dot Z of P is a price vector, PL, and excess demand function vector from Z1 to ZL. And the dot product between these two vectors is going to be P1, Z1 plus P2, Z2, all the way to PL, ZL. So summation of PK, ZK over K. Okay? So the P dot Z of P is going to be 0. That is Waller's law. So one implication of this Waller's law is P dot Z of P is always equal to 0. And one important implication is, suppose we have two goods. Okay? Then Wallace law requires P1 Z1 and P2 Z2 is always equal to 0. Okay? And suppose that in market 1, so where commodity 1 is traded, we have neither excess supply nor excess demand. So Z1 turns out to be 0. Okay? So market clearing occurs in market 1. And by Wallace law, market 2 should be cleared automatically. It should be 0 as well. Okay? Because the dot product must be 0. If we have a market clearing in market 1, in market 2, the market 2 is automatically cleared. Okay? That is one important implication of Wallace law. Okay? In case of L markets, now P1, Z1, P2, Z2, and PL, ZL. If we have a market clearing in L-1 markets, so we know Z1, Z2, and up to Z sub L-1, Z sub L-1 are all equal to 0. Okay? And the last remaining market, Z sub L, excess demand function, there is no excess demand and no excess supply. So it should be 0 as well. All right. So although we have in terms of degree of freedom is L for this equation because we have L variables from Z1 to ZL. Okay? But once we determine that first, L-1 components, and those are, equal to 0, and the last element is automatically 0. In fact, the degree of freedom is not equal to L of L-1. That is one important consequence of Wallace law. Right. And the last two properties are quite immediate, quite straightforward. Excess demand function should be bounded below because Z of P is nothing but demand function minus endowment, initial endowment. But if some goods are useless, right? So in case of local non-satiation, or price is really, really high, so nobody can afford any goods, then X of P is at most 0, right? It cannot be negative value. So excess demand function must be higher than, because this X is a positive value, must be higher than negative, this is a typo, negative initial endowment. And so no matter what this P, even though P is really high, still Z of P is higher than negative of initial endowment. And the first one, the last property, is a little bit complicated. The proof is a little bit complicated, but the underlying idea about the last property is really simple. Suppose that some good K is equal to 0, and excess demand function at that price, so excess demand function for good K must go to infinity under the assumption strong monotonicity, right? If good K is desirable, and then the price of a good K is almost equal to 0, and this demand function will diverge to positive infinity. So the excess demand function also diverges to infinity. All right. So with those four properties, now in the next video, I'm going to explain this numerical example. So how to drive Walrasian equilibrium in 2x2 exchange economy. And let me just explain one more slide before finishing the first lecture video. So we just explained the pure exchange economy, but the same idea can be extended to general framework. So private ownership economy. So in the presence of production, now the only thing we have to do for construction of excess demand function is now we should think of a profit maximizing production plan for each from J. Okay? So the excess demand function can be defined as consumer I's demand, so aggregate demand for good K, minus aggregate supply. But in the presence of production, not just initial endowment, we have to take into account some production. Okay? So YKJ star, summation of YKJ star over J. Okay? So that is a total use of commodity K by firms or total output of a good K produced by J firms. Okay, so these two will be total supply. So the aggregate excess demand, just the aggregate demand and aggregate supply. Okay? We have to amend a little bit, but it's not that much. I mean, the underlying idea is the same. And the consumer I's wealth is also slightly changed. Not just the market value of the initial endowment, E dot omega I and plus theta Ji E dot Y star J. Yeah. Once again, because in this economy, private ownership economy, each consumer has a share in firm J, theta Ji. Consumer wealth is going to be market value of his initial endowment and some profit from holding shares. Right? And then using this, we can define excess demand function. And then we can think of the aggregate excess demand function is the L tuple vector, excess demand for each commodity K. And then Walrasian equilibrium price vector is going to be characterized by this system of functions, the system of equations. When theta I is strictly convex and strictly monotone, strongly monotone, when strongly monotone, then the P star is characterized by this equation. Z of P is equal to 0. If we have just a local non-satiation, then this is going to be inequality. Alright, so I explained in this video several things. So we went over the definition of Walrasian equilibrium, and I introduced the excess demand function. And using that function, I provided one sufficient and necessary condition for equilibrium. That is a Z of P is a non-positive value, and P is going to be Walrasian equilibrium. And I explained the several properties of excess demand function. Okay, hope you guys enjoyed this video. Oh, I took 1 hour 15 minutes. Oh my gosh. Yeah. So hope you guys enjoyed this video. Then I will explain this numerical example in the next one.